So we are going to look at the architecture of molecules. So the architecture of molecules is basically the structure of molecules in like their occurrences, how they look like when bonding takes place. So we are going to look at the Lewis structure, which we looked at yesterday. Now this is where we have covalent bonding and the geometries of these molecules. So like I said last time, there is a theory called the Vespers theory, valence shear repulsion theory, where we look at molecules and the orientation in space with angles. Like not only did we do the ones on hybridization à l'état sp3, sp2, sp with 109.5 degrees for sp3, 120 degrees for sp2, and 180 degrees for sp. We're going to find that there are molecules that also have maybe say it's 105 point maybe 0.2 degrees. So different variation of angles in space, how molecules are arranged in space. So first definitions, that is the formation of covalent bonds, then regular octet, then limits of the octet rule, oxidation numbers, then construction of Lewis structures. So the definition, what is a covalent bond? First of all, what's a covalent bond? What's a covalent bond?
Covalent bond is a type of bond that occurs between elements of non-metals.
Voila. So a covalent bond is, in other words, a covalent bond is one that involves the sharing of two electrons by two different metals. Now, not metals, sorry, non-metals. So covalent bonding is basically the sharing of electrons by two non-metals. That is covalent bonding. And one of the properties that you have learned so far of covalent bonding is that when it comes to breaking of these bonds, the energy that is required for you to break the bonds in a covalent bond is less than the energy you would need to break a bond in an ionic liaison. So covalent bonding is the easiest type of bond that you can form from elements of the periodic table, that is the metals. But in a case where you are going to study ionic bonding, ionic bonding is the other type of bonding that requires a lot of energy for you to break the liaison. So the reason behind why it is hard for you to break a bond is because there is an electrostatic force of attraction that exists between two opposite charges for a positive and a negative charge. Because of that opposing force that exists between the two, the energy that you need to break those bonds will be high as compared to the ones that are sharing electrons. Because once they are sharing electrons, energy that you require to break those bonds will be minimal. It won't be as much as that for an covalent bond. Then you also have metallic bonding. Now, for metallic bonding, this is just the metal itself and its delocalized electrons. So for metallic bonding, we just use that to just show that in metals, we have electrons that are delocalized. And because of the delocalized electrons, we have the conductivity of electricity. Because the conductivity of electricity is done by the electrons. I don't know if you guys know that. The conductivity, like a metal conducting electricity, it's because of the electrons, because of the presence of electrons. That is why we have the conductivity or metals conducting electricity. It's because of the delocalized electrons. So in the covalent bonds that we're going to look at, maybe just start explaining from these things here. So that's just to do with the formation of covalent bonds. Then we have regular octet. Now, regular octet is just a rule. It's just a rule that now there's one thing you're supposed to take note. There's what you call a regular octet and regular. I don't know how you can pronounce this word. D U T. Duet, like when you have the helium atom. The helium atom is the only atom on the periodic table that has a duet configuration. So what I mean by duet is that you have 2 electrons there. If I say octet for helium, it won't make sense because helium only occupies 2 electrons in its outermost shell. That is the maximum number of electrons that it can occupy. Now, if I say the octet rule for the octet rule stands in for all noble gases, I'm correct, yes, but helium is not amongst those that obey the octet rule, but it obeys the duet rule. So the octet rule or the duet rule is basically that all noble gases are supposed to occupy the maximum number of electrons in their outermost shell. So you find that there are elements of the periodic table that do not satisfy this hypothesis. There are those elements that do not support this hypothesis when they are bonded to different elements. For example, when we come to the limits of the octet rule, you find that some elements, for them to have a stability, for them to be stable, they will not abide by the octet rule, but rather apply something else for them to be stable. So basically, the octet rule is a rule that states that an element on the periodic table or an atom will always look for stability. Now, stability is having the octet kind of like looking alike like the transition method, no, the gas ray. Gas ray is the noble gases. So, like you learned from your chemistry back home, you say that non-metals and metals. The non-metals will always lose electrons, or will always gain electrons. Why? Because they also want to suit the argons and all those things, the noble gases. Same applies to the metals. Metals will always lose electrons because they want to be like noble gases. That being alike, like what metals want to be like the noble gases, what non-metals want to be like the noble gases, is what we are calling the octet rule, because they want to satisfy that rule, that is, they are supposed to occupy the maximum number of electrons in their orbitals. That is in the case of the metals and the non-metals. So when you look at maybe we go octet. So when you look at an example here, we're going to start with a simple example first of all. So in yesterday's example, we're going to use fluorine. So fluorine, we're always going to use Lewis structures to just represent the octets and thingy. So we are saying fluorine will always have how many electrons in the outermost shell? In its atomic state, it will have that is 7 electrons. Now, for it to gain stability, for it to attain the octet stability, now this is in its atomic state. Now, for it to attain its octet stability, it's supposed to gain an electron, isn't it? It's supposed to gain an electron. So if it gains an electron, it now becomes an ion. It now becomes an ion. It now becomes an ion of charge more. So fluorine has obeyed the octet rule. Fluorine has obeyed the octet rule. So in the case where fluorine wants to form a double liaison, no, not a double liaison, a covalent bond, sorry. If it wants to form a covalent bond, what happens? You have say star there, another star there. Then, so we have 1 electron like that. So at the end of the day, you're going to have the sharing of these 2 electrons. So when you count, you find that when you count, you guys have done this before, it's just a review. When you count, you say 1, 2, 3, 4, 5, 6, 7, 8. You find that this atom here, fluorine, the first one here, has obeyed the octet rule. It has obeyed the octet rule in the sense that when you share the electrons, that is in a covalent bond, this here had the maximum number of electrons in its outermost shell. Same applies to the other fluorine on the other side. We have 1, 2, 3, 4, 5, 6, 7, 8. Therefore, it is also obeying the octet rule by the sharing of electrons. This is the formation of covalent bonds. Now, there are cases where the octet rule does not apply. The octet rule does not apply. So I can also give an example for maybe hydrogen. So hydrogen will form 2. This is 1 there, and another one there like that. A liaison like that. So this is not an octet, but a duet. Because it satisfies what helium's electron configuration looks like. That is with 1 s à la puissance 2. À la puissance 2. So it is found that almost all nonmetals obey when they are bonded to themselves. When for example, fluorine bonds to itself, if they form, like example I can give is if they form diatomic molecules, that is fluorine, chlorine, bromine, astatine, and iodine, all those things, if they form diatomic molecules, the octet rule is going to be satisfied. But there are cases where the octet rule does not apply. There are examples where the octet rule does not apply. So I'll give an example of one which is not applicable. This is an exception to the octet rule. This is an exception to the octet rule. So you have an example of aluminium hydride. So this is an exception to the octet rule. Now, how is it an exception to the octet rule? So you find that aluminium being the center of this molecule compound, you're going to have a hydrogen per mole. We're going to have a hydrogen on top, a hydrogen on top there, another hydrogen occur, another hydrogen occur. So how many atoms does aluminium have in its outermost shell? How many atoms or electrons does aluminium have in its outermost shell? Aluminium is in group what, first of all? Aluminium is in group what?
Group 3.
It's in group 3. So if it's in group 3, how many electrons are supposed to be found in the outermost shell?
3.
Eh?
Hmm?
If it is in group 5 or 3, how many electrons are supposed to be found in the outermost shell? Aluminium.
5.
5, isn't it? Isn't it?
Yes, it is what it is.
Hmm?
Yes.
Exactly. So now, in this case, you will find that 1 electron of aluminium will bond with 1 of hydrogen. 1 electron of aluminium will bond with another hydrogen, and 1 electron of aluminium will bond with another hydrogen. So when you compare these two molecules, there's this one I'm going to write here, and the other one that is going to stand in for what we are just from saying here. If aluminium has how many electrons in the outermost shell? So we have 1, 2, 3. Now kuna 5, right? We have hydrogen there. We have hydrogen there. You have hydrogen there. So this hydrogen contributes this. This other hydrogen contributes this. And this other hydrogen contributes this electron. So if you to count how many? 1, 2, 3, 4, 5, 6, 7, 8. So between the two molecules here, it is found that this one is unstable. It is found that this one here is unstable. So like I said, was it in organic? No, it was yesterday in Générale. I said an atom will always find, or an electron will always find the easiest route more comfortable than the one that is going to be ambiguous, that is going to cause the atom to be unstable. Now, in this case, this one here that should obey the octet rule. This one is supposed to obey the octet rule. Now, it is found that this one that obeys the octet rule is not stable. So an atom or a compound will always want to attain stability. An atom or a compound will always want to attain stability. Now, in our case, when we want to look at a compound that is in its stability form, we are going to consider this one here. So this would be aluminum hydride, which is this one. Now, where does the exception come in with octet rule? It does not satisfy the octet rule in the sense that when you count the number of electrons that aluminum has here, aluminum has only 1, 2, 3 electrons, and is also sharing other 3 electrons with hydrogen. So at the end of the day, you find that aluminum has 1, 2, 3, 4, 5, 6. It has 6 electrons that are being shared by hydrogen and aluminum itself. And an octet should have at least a maximum of 8 electrons. An octet, it's an octet. So it is found that this one here shares only 6 electrons, and it is stable in this form, and not this one, Here, if we were to apply the octet rule, it works out properly. We're going to have 8 electrons. We're going to have 8 electrons for the aluminum, and we also are going to have a balance 2 electrons for the hydrogen, a balance 2 electrons for the hydrogen, a balance 2 electrons for the hydrogen. But what I'm saying is, an atom or a compound will always want to attain stability. An atom or a compound will always want to attain stability. Now, between the two, between this one here and this one, it is found that the one that has 6 electrons being shared between hydrogen and aluminum is the most stable as compared to this one. And therefore, because it has got 6 electrons, other than 8. Because it has 6 electrons other than 8, we are going to find out that this compound, that is aluminum hydride, does not obey the octet rule. That is, it does not obey the octet rule. So an example would be also, what is this? Is it bromine hydride? Bromine hydride. Bromine is number 5. Aluminum is it's below bromine. So it is found that because they are in the same, because we're just going to use periodic trains, I won't draw the structure, but because of periodic trains, the same group almost have the same trains. So if aluminum possesses this type of orientation, it is the same principle that we are going to apply. Maybe if I just draw it. So bromine is also in group 5. For it to attain stability, it's supposed to gain 5 more electrons. Which is the correct way over the bromine molecule. Let me just draw the bromine atom here. Sorry, not molecule, atom. This is the Lewis structure for bromine, isn't it? This is the Lewis structure for bromine. So it needs how many electrons? It needs 1 more there. It needs another one there. It also needs another one there. It also needs another one there and another one there. So this bromine Yeah, not bromide. Boron, sorry. Boron. Not bromide. Boron. Boron. So this boron atom needs 5 more electrons for it to attain stability. Now, this here is an ion. It's an ion. So it has gained how many electrons? It is supposed to gain 5 more electrons for it to attain stability. Now, this here has satisfied the octet rule, which states that all atoms on the periodic table always want to attain stability. That is either by gaining of electrons, that is in the case of nonmetals, or by losing electrons in the case of metals. So this is a nonmetal and it has gained electrons and it has satisfied the octet rule. Now, when we want to apply the octet rule on a hydride like this one, this one here. So we are saying boron has a Lewis structure of 2 pairs of electrons and 1 lone pair. This one is alone, so it's called lone because it's alone. It's not paired to anything. So these are called paired electrons. And the ones that are not involved in any type of bonding or the ones that are alone are called lone pairs. So we have a hydrogen there, another hydrogen there, another hydrogen. I'll put another one there. So if we want to share the number of electrons so that we have stability between the atom of boron and the hydrogen atom, that is in the case of a covalent bond, because in a covalent bond, like I said, we are just sharing electrons. We are just sharing electrons. So if we share the electrons here, we're going to have another hydrogen atom contributing this electron, another hydrogen atom contributing this electron, and another hydrogen atom contributing this electron. Now it will be found that the hydrogen has attained stability. The hydrogen has attained stability. That is the duet regular duet, which is also, you can also call it the octet rule. But to just show that the octet rule only stands in for atoms starting from is it neon to the last one on the noble gases. Maybe is it krypton? The last one, xenon, somewhere there. So it stands in for those atoms. But for helium, we are going to call it a duet because it only has 2 electrons that it can occupy as maximum. So now the same principle, that is, if the the boron atom has 2 electrons, that is 2 electrons that are not involved in any type of liaison, it is found that this atom will be very, very unstable. It will be found that this atom will be very, very unstable. And therefore, because it is unstable, boron hydride will resort to forming what you are seeing here. It will resort to forming what you are seeing here. And if you were to count the number of electrons that are being shared, that is for boron and the hydrogen atoms, you're going to find that it's 1, 2, 3, 4, 5, 6. So there are 6 electrons that are being shared. Now, the octet rule is we are supposed to have at least 8 electrons being shared. At least 8 electrons being shared. In the case, I don't know if you guys saw the example I gave for fluorine. There are supposed to be 8 electrons being shared. There are supposed to be 8 electrons being shared, and not how many? Not 6. Anything different from 8 does not apply to the octet rule. Are there any questions?
Yes, I have a question.
Yeah.
What on the aluminium, the one that you gave?
Yeah.
You said aluminium has got 5 electrons in the outermost shell, and 3 are involved in bonding with the hydrogen. then where are the two? Where are they going? Would it just get rid of them, or they're just not sure, or what?
Okay. I said aluminium has got how many electrons in the atmosphere?
You said 5.
I said 5.
Yes.
I said aluminium has got 3 electrons in the outermost shell. 3 electrons in the outermost shell. And it will gain 5 for it to attain stability. That's what I said. That's what I said.
That's not what I heard.
That's what
I
you
heard
heard.
that it's got 5. No, me, I didn't hear that. I heard that it's got
Above.
5.
No, I asked
So
where.
3 were involved.
No, I asked where aluminium was found on the periodic table, and you guys said it's found in group 3. So if it's found in group 3, it means it has got 3 electrons in the outermost shell and needs 5 more electrons for it to attain stability. It needs 5 more electrons for it to attain stability. So now the question where you are saying what happens to the other 2 electrons? The 2 electrons here are going to remain. The 2 electrons are going to remain. Of course, it's supposed to be. Of course, the 2 electrons are supposed to remain here, but okay. So of course, the 2 electrons are going to remain here. But in the sense of explaining that this aluminium does not apply on the octet rule, we are supposed to overrule the electrons there. We are supposed to overrule the electrons that are going to be found there. Now, the octet rule comes in when there is sharing of electrons. Please get me correct. When there is a sharing of, when the electrons that are being shared, and when you count the number of electrons, like we saw for fluorine, I'll just give, so 1, 2, that. So when there's a sharing of electrons, when you count 1, 2, 3, 4, 5, 6, 7, 8, the electrons are being shared. The electrons are being shared here, and it is satisfying the octet rule. Now here you only have 3 hydrogen atoms that are sharing electrons with this aluminium here. Only three, and therefore when you count how many are being shared, and applying the octet rule, you find that there are only 1, 2, 3, 4, 5, 6. Now for this one, we have 1, 2, 3, 4, 5, 6, 7, 8. Is it making sense?
Yeah, it is.
Yeah.
I
So
have a question. You've said aluminium has got 3 electrons in the atmosphere, right?
Exactly.
Yeah. Why isn't it just losing the electrons other than gaining 5? Because, for example, if we have sodium, which has got 1, right? We won't say that it will gain 7 electrons, but it will lose 1. Isn't it not the same case where aluminium, which has got 3 electrons, it will just lose the 3 for it to have 8 rather than gaining 5?
Okay. That's a very good astuce. Now the thing is, aluminium on the periodic table, where is it found? Aluminium. It's found. Okay. So aluminium is found on the other side of the periodic table. It's found on the staircase line. So it's found on the staircase line. And what property do you guys know about the staircase line? Just one property you know about the staircase, a very important one.
They have both
Really?
non-metal and metal qualities.
Exactly. It has got a non-metal and metal qualities. So these elements that you're seeing here are called metalloids. These elements you're seeing just close to the what is this? The staircase line. They're called metalloids. So they can possess in when you apply it in is it chimie en solution, we call these elements here that amphoteric. I don't know if you guys have heard about amphoteric compounds. Amphoteric compounds. This is where you have a compound that is behaving as a base in an acidic medium and is also behaving like an acid in what's this? And it's behaving like a base in an acidic, and it's behaving as a base in the other solution. So in what I'm trying to draw here is that aluminium can exist in those two forms. Aluminium can either lose 3 electrons or can also gain 5 more electrons. It can lose 3 electrons or it can gain how many more? How many more electrons? It can gain 5 more electrons. Now in our case, we have aluminium that is going to have 5 more electrons. We have aluminium that is going to have 5 more electrons. And moreover, what we are forming here is not an ionic bond. We are forming, where was I? What we are forming here is not an ionic bond. Please take note. What we are forming here is not an ionic bond. What we're forming here is a covalent bond. It's a covalent bond. And we said all covalent bonds are supposed to be formed by nonmetals. Now, in this case, aluminium takes the form of a nonmetal. Now, if it takes the form of a nonmetal, it means it is supposed to gain how many electrons? That is 5 electrons. Now, from the 5 electrons that it's going to gain, only 3 of those are going to be used for the hydrogen. That is the sharing between the hydrogen and the aluminium itself. Then 2 will be left out. 2 will be left out. Now we are saying the atom will always be stable in that form I gave. Is it clear, Mr. Tid? Or you still have an argument?
Okay, I'll just come back to you later.
Okay. So the idea is aluminium is a metalloid. Aluminium is a metalloid. So at some point it will behave like an nonmetal. At some point it will behave as a metal. Now in your case we have the sharing of electrons. Now aluminium will exhibit the non-metallic state. It will exhibit the non-metallic state, and therefore other than losing electrons, it will rather gain electrons and share those electrons with an atom of so this would be the structure of aluminum hydride. Therefore, it will not obey the octet rule. That is in the case where it will have that is 5 electrons in the outermost shell. It will not obey the octet rule because it will be found that only 6 electrons are sharing liaisons. Only 6 electrons are sharing the bonds. Only 6 electrons are sharing the bonds. Then, per contre, when you look at the example I gave on fluorine, it is found that 2 electrons are sharing 2 electrons, or maybe let me say, fluorine has got 1 electron that it's looking for it to attain stability. And you find that fluorine on the other side also gives it another electron and now forms a complete liaison. It forms a complete liaison, It forms a complete liaison. And therefore you find that at the end of the day, the fluorine atom or the fluorine element there really satisfies the octet rule in the sense that the number of electrons that are being occupied at the end of the day is going to be 8. D'après la partagement, but where there is a sharing of electrons, So I said, when you compare this atom or maybe say compound to aluminum hydride with another electron there, this one here is very unstable. This one is very unstable. So like I said, atoms specifically will always want to be in a stable form. Atoms will always want to be in a stable form. Yeah. Am I making sense?
Boss, question.
Yeah.
I don't know if I heard you correctly. You had said the other electrons, we have to leave them out. But will it be stable? Like, will it attain a noble gas electron configuration if we leave them out?
No, the idea is on the periodic table, like I said, the idea is, like I said, on the periodic table, there are elements that obey the octet rule. There are elements that obey the octet rule. Now, in this case, aluminum hydride does not obey the octet rule. It's one of those exceptions that does not obey the octet rule. The octet rule, which is all elements or all atoms on the periodic table are supposed to satisfy the, what do you call it? The noble gas configuration. They are supposed to satisfy the noble gas electron configuration. But in our case, aluminium does not satisfy that rule. It will only be stable in this state. It will only be stable in this state. Even though we want to take it in the noble gas configuration, it will be found that in the noble gas configuration, it will not be stable. It will not be stable. In other words, what I'm trying to say is, you have sodium, let's say sodium. If I explain it this way. Sodium has got how many electrons? Sodium has 11 electrons. Sodium has 11 electrons. So for sodium to have, what do you call it? An octet state, it's supposed to lose how many electrons? It's supposed to lose an electron for it to have a 2,8. That is for neon. Now, this is the octet rule. This is the octet rule. Now, here, sodium is stable. Right? Now, what I'm trying to say for aluminium, I'll use sodium as an example. With 2,8, one, like that. I don't know, let me use comma 7. Something like this. So now there are two examples here. I'm going to use sodium, then picture it in the case of aluminium. So this is the octet rule. This is the octet rule. Are we in agreement with this? This is the octet rule. Are we in agreement?
Yes, it is.
Yeah, this is the octet rule. This is the octet rule. This is in other words, this is an atom of neon, because neon has got 2,8 configuration. Now we are saying aluminium in our case does not obey the octet rule. So aluminium, when aluminium in the aluminum hydride forms an octet, it is unstable. When it wants to form an octet, it is unstable. But in a case where it does not obey the octet rule, because this is not the octet rule here, are we in agreement with this one? This is not the octet rule. The 2,7 for sodium. It's not the octet rule, isn't it? Are we in agreement? It's not the octet rule. Now, in the case where it does not obey the octet rule, aluminium is stable. Now, I'm saying atoms will always want to attain stability, the easiest way out. Now, it is found that aluminium will take the stable way other than the unstable octet way. Have I made sense there with this example? Eh? Have I made sense here?
You're trying to say it can only for it only uses the covalent bonding. Also, is that what you're trying to say?
Yeah. Pardon? What's your question?
I was a little bit confused here in that those 5 electrons that are found in the outermost shell of aluminium. So as we are bonding with hydrogen, we're bonding with hydrogen here in a covalent bond.
Exactly.
Yes, but here, so we don't complete it. Like, is that what you're trying to say?
Exactly. That's what I'm trying to say. We are not completing it with the octet rule. We are not completing it with the octet rule. Why? Because it is found that when aluminum hydride wants to attain the octet rule, when aluminum hydride wants to attain the octet rule configuration, it is found that the aluminum hydride is unstable. It is found that the aluminum hydride is unstable. But in the case where it forms only 6 electrons, it only shares a maximum of 6 electrons. It only shares a maximum of 6 electrons. It is found to be stable. It is found to be stable. That's the example I've given here. So in the case where you have sodium with an octet here, you have sodium with an octet. Sodium has an octet of 2,8. That is an octet. We understand that that's an octet. Now, in a case where this octet, we are saying the octet is supposed to be stable. In all cases, the octet is supposed to be stable. In all cases, all noble gases are stable. All noble gases are stable. Then you have this sodium here with 2,7. Normally, this one here is unstable because it does not satisfy the octet rule. But it is found that it's the opposite. Those that want to satisfy the octet rule, in the case of aluminum hydride, will not be formed. It will not form. It will not form. In the case where it wants to satisfy the octet rule, it will not be formed. But in the case where aluminum hydride forms under the octet rule exception, where it forms under the octet rule exception, it will be formed and it will be stable. In other words, when it forms the octet, the aluminum hydride is unstable. But when it forms the one that has 6 electrons, it is very stable. It is very stable. Am I making sense?
The one which is covalent is more stable.
No, this one here.
That's the one that's more stable.
Yeah, this one is more stable. No, as in, you guys, are you following? It's an exception. It's an exception to the octet rule. It's an exception. It's an exception. It means it does not apply the octet rule for it to attain stability. It only applies its own rule. There's another rule that you're supposed to apply for it.
Oh.
Yeah, exactly. It's an exception.
Okay.
Yeah, it's an exception. Please take note. It's an exception to the octet rule. It's an exception. Exception to the octet rule. It's an exception to the octet rule. Is it clear for everyone?
Yes, it's very clear.
Yes.
Okay.
Question.
Uh-huh.
So is boron and aluminium the only elements that exhibit such a property, or there are others as well?
No, there are others. There are others. So I can give an example of these. What is it? I can give an example of what is this going on? You have xenon. When it forms an ion. So when you do the configuration electronic, when you do the Lewis structure for these 5 electrons, let me just try to draw it. So how many electrons is xenon supposed to have in the outermost shell? Hmm?
8.
Are you sure, Mr. Ted? Eh? Are you sure? How many electrons is Xenon supposed to have in the outermost shell? Let me just do this to just simplify this.
Must have 8.
Just to,
Yeah.
just to simplify this. Let me say, just a minute. Let me just, so that we don't waste time. Where is it? Where is it? Okay, yeah. Just a minute. I share. Just share your screen fast up. Can you guys see the xenon structure? Fast. Can you see it? Can you see?
Yes.
Yes.
Okay, I think this one is better. Yeah. So, no. Okay, I'll get back to this one later on. So we use this one first. So we are saying for us to apply the octet rule, we are supposed to satisfy non-contef, isn't it? So
Yes.
fluorine has got how many? 1, 2, 3, 4, 5, 6. It has 7 and 8. N'est-ce pas?
C.
Oui. Then it applies fiancé, it applies conseil. It's the same thing. This year. They all have 8. They all have 8. Now, you find that there's one electron that is being shared already with this one. So you already have 2 that are sharing. This is a covalent bond. Please take note. It's a covalent bond. So when you're counting, that is, for xenon, you're going to count 2, 4, 6, 8, 10. And you have 2 already that are not bonding there. Is it making sense? When this is it's a covalent bond, and when you're calculating or counting for a covalent bond, we take into consideration the number of electrons that are being shared. So we know that this straight line here, there's one electron there, and there's another electron there that are forming this liaison. So when you're counting, you count 1, 2, 3, 4, 5, 6, and 8. This whole line here represents 2 electrons. That is 1 electron from fluorine and another electron from xenon. Est-ce que c'est clair? There's one electron from fluorine and another electron from xenon, and they are sharing. It's a covalent bond. So when you're counting, you'll be like 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Because kulika kamo is 7 apa naka 8. There is one electron from fluorine and there's another from xenon, which applies for all these 5 electrons, for all of them. 1, 2, 3, 4, 5. Now, when you were to count, if you were to recount, you find that for xenon now, in the case of xenon, you find that when you count here, you're going to have 2, you're going to have 4, 6, 8. It was supposed to, if it was supposed to end here, it was supposed to end here for us to satisfy the octet rule, But you find that it continues, and you have 10 there, you have 10, and you also have 2 electrons that are alone, that are not pairing in anything, that are not pairing in anything. So it is found that this one here, this atom, or maybe say compound of xenon, is it pentafluoride with an ion of minus, it is formed as stable as it is in this state. It is formed in a stable state, as you can see it in this diagram representation here. So this one is also an exception to the octet rule. Why? Because it does not satisfy the number of electrons that we are supposed to occupy in the outermost shell, which is 8, like Mr. Teddy said. Now we have 1, 2, 3, 4, 5, 6, 7, 8. Normally, we're supposed to end here. We're supposed to end with these 4. But even though we end with these 4, we still find that there are 2 more electrons here that alone. There are 2 more electrons that alone. The covalent bonding is a sharing of electrons. Sharing of electrons. These ones are supposed to be shared also. These ones are supposed to be shared. So that at the end of the day, we have an octet. So that at the end of the day, we have an octet. But in the case where we do not satisfy the octet, but we have the formation of different compounds, that implies that the octet rule is an exception to those compounds. It is an exception to those compounds. Am I making sense? Is that a very quick question?
Yes.
Is it making sense now? Is it making sense? There are a lot of examples. That yeah, it's making sense. Eh? These elements that you're seeing are exceptions. Eh? They do not define the octet rule. They are not defined by the octet rule. I don't even know the name of the rule. Maybe we can call it the Moléculaire rule. But it does not satisfy. It does not satisfy the octet rule. The octet rule. An octet is 8 electrons maximum. 8 electrons maximum. Now it is found that in the covalent bond of xenon pentafluoride, you have 2 electrons that is there.
It's
2,
11 o'clock.
4, 6, 8, and 10. There are 10 electrons that are being shared for xenon and fluorine. For xenon in reference to fluorine. And there is 2 more that are not shared. There is 2 more that are not shared. And therefore, when you look at this compound, you find that it does not satisfy the octet rule. It does not satisfy the octet rule, but satisfies another rule. It satisfies another rule. Now, because we are saying all compounds are supposed to satisfy the octet rule, whatever does not satisfy an octet rule is now what we are calling an exception to the octet rule. Nafingira nafijama. Is it clear?
Yes.
Yes.
Now, how do we know these elements as to which they don't obey the octet rule?
How do you know? No, on that one I would lie. Why is that? On that one I would lie. But basically, what you're supposed to do is, like I said, in a covalent bond, you are supposed to have the satisfaction of the octet rule, isn't it? You are supposed to have the satisfaction of the octet rule. Now, in a case where an element is bonding and does not satisfy the octet rule, it it becomes an exception. I wouldn't point out an element and say, okay, this one you will never have an octet formed. No. There are cases where, for example, if I have in a xenon, if I was to remove 2, maybe let me say how many. If we have 1 here that's going to bond, if I remove two of these, what's this? If I remove, I'm not even removing. If I add 2 more of the fluorine, 2 more fluorine, 2 of the fluorine, I still want balance. It still won't balance because our maximum is supposed to be 8. So if I say, okay, let me say 1, 2, 3, then 1, 2, 3, 4. So this is 8 already. 1, 2, 3, 4, 5, 6, 7, 8. So if I remove this one here and I do not have these 2 electrons, it means we have obeyed the octet rule. I hope you're getting the sense there. If I remove these 2, if I just forget about these 2 electrons and forget about this fluorine atom also here, it means I have obeyed the octet rule in the sense that you're going to have 1, 2, 3, 4, 5, 6, 7, 8 electrons that are being shared equally. But in our case, we are finding that this one here does not obey the octet rule because the number of electrons that are being shared has already passed 8. The number of electrons that are being shared has already passed 8. In our case, we have 1, 2, 3, 4, 5, 6. So that is 12 plus these 2 here, we have 14. So we have 14 electrons, if I'm not mistaken. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. Not 14, 12. 12 electrons. That is for the xenon and the fluoride, which is not equals to 8 electrons. But in a case where an atom satisfies 8 at 8 electrons. 8 at 8 electrons. 8 electrons. That has satisfied octet rule. Or maybe say 2 electrons to 2 electrons. That is for the Joule regular. So is it making sense? These are exceptions to the octet rule. They are exceptions to the octet rule. Is it making sense?
So that is what you're trying to say is that the electrons that we've counted, all the electrons have to be shared equally, saying the way you give for like fluorine in the
And
in
they
the
are
first
supposed.
example. In the first example, gave fluorine because this one donated 1 electron and the other one, so they actually, that 1 electron was like
Completing
made
the
2 of
octet.
them, meaning they were all shared. Yes.
It was
So
completing the octet. If it does not complete
Yes.
an octet, it becomes an exception to the octet rule.
Okay.
Exactly.
Okay.
It's
Now,
making sense now, eh?
okay. Yeah.
Exactly. Is it making sense for everyone?
Yes.
Okay, alhamdulillah. Then, if it's making sense, we just go to the last part of this. This is oxidation. You guys know how to calculate oxidations? You guys know how to calculate oxidations?
No,
You don't?
I'm speaking for myself. I don't.
Guys, ikue suppose inafungwa sila but even hours ikue. Okay, I'll just show you how many examples. Let me say, I'll just show you maybe 2 examples of how to calculate oxidation. So, an example would be, I'll give the sulfate anion, and what else? I can also give the, what else? Say, copper 2 sulfate, to just make life a bit easy. No, copper 2 sulfate is one, I guess. So when you're calculating oxidation numbers for different, an atom, a radical, etc., there are rules that you're supposed to apply. I'll be quick on these ones. For an atom, it's always neutral. So for an atom, it's always equals to 0. If it's an ion, the oxidation number is equivalent to the charge that the ion forms. If it's copper 2, if it's copper 2 plus, it will be called the oxidation number will be equals to 2. The oxidation number will be equals to 2. If it forms a +1, the oxidation number will be equals to 1. Then for radicals, you're always going to equate the oxidation. So this one is saying if it's an ion, it's going to be +2. If it is an atom, just an atom, it's going to be equals to 0. Then if it's a compound, for example, sodium chloride, it will also be equals to 0. For compounds, equals to 0. So when you're calculating for radicals, or radicals more especially, like the sulfate radical, you are always going to equate the charge over this radical. Like you're going to equate the sum of the charges for the sulfur and for the oxygen equals to the charge of the radical. Like this is going to be a unit charge. So in other words, what I mean is you're going to say -2 is equals to the oxidation state for sulfur plus the oxidation state for oxygen, like that. So oxidation states, in some instances, they might mean the valency electrons. In some instances, it might not mean the valency electrons. Now, in our case here, the oxidation state we are going to consider will be the valency electrons. So questions might come to say calculate the oxidation state maybe for sulfur in the sulfate anion or in the sulfate radical. It can also come to say, okay, calculate the oxidation state for oxygen in the sulfate anion. So in our case, we are going to calculate the oxidation state for sulfur in the sulfate anion. So we are saying we are going to equate the unit charges for the sulfate plus the unit charge for the oxygen equals to -2. This -2 here is what you are seeing. Is what you are seeing. So now we're calculating for sulfur in the sulfate. So this is just simple arithmetic. So we are saying in some instances, the oxidation state for atoms might be equivalent to the valences. It might be equivalent to the valences in some instances. In some instances, you find that it's not equivalent to the valency electrons because copper is a transition metal, and we know that one of the properties of transition metals is that they form variable valences. Now, you wouldn't say that the copper here is going to have a 2 always, no? The copper can have 1, it can have a 3, depending on the oxidation state that it is undergoing. Depending on the oxidation state, it can have anything. It can have anything depending on the oxidation state that is being taken into consideration. So in our case, if we're calculating for sulfur, simple arithmetic, this 4 0 or 4 oxygen goes on the other side. So you're going to have sulfur is equals to Singa. See, sulfur is equals to what? Eh? Sulfur. When to calculate for sulfur? When you do arithmetics, what happens?
It will be -2 minus 4 0.
-2 minus 4 0. No, there's 0. There's 0. Hey, oxygen. Oxygen. So now we are saying for this question, we are going to take the oxidation state for oxygen to be -2, which is also the same as the valency, which is the same as the valency for oxygen. And therefore, when we calculate, we're going to have -2 minus 4 fois -2, which is going to give how many? +6 plus 6 plus 6. So this is oxidation state for sulfur in the sulfate. Then how you prove this is just by doing the same thing. You just add foot. If it's going to give you -2, then you are correct. If it doesn't give you -2, then you are wrong. So sulfur, that's +6. This is what? Plus 4 minus 2. We're just doing this, eh? Trace the page. Now we're just replacing. So how many does it give?
-2.
Exactly. So it gives -2. Gives -2. Gives -2. So therefore, the oxidation state for sulfur in the sulfate is -2. Then we calculate for copper in the sulfate. So same thing, eh? So it's going to be copper plus sulfur plus 4 oxygen. Because it's a compound, the unit charge will be equals to 0 because there is neutrality. Like the charges have cancelled each other, so it is neutral. It is equals to 0. So we're calculating for copper. Yaraba copper copper is equals to, when this sulfur goes on the other side, minus sulfur minus oxygen, like that. So in this case, we are going to take the oxidation. We've calculated the oxidation state for sulfur in the sulfate. Sulfur in the sulfate to be 6. So it will be minus 6, or maybe a positive 6 like that. Positive 6 minus 4 minus 2. So when you do arithmetic, what you have minus 6 plus 8. Minus 6 plus 8 is what? Minus 6 plus 8, Shinga. Positive 2. Positive 2. And therefore, if you want to prove this on call, you do the same thing. Hope you are following it. I'm here, now come and write here. So it must give us 0 at the end of the day. So we are saying that's copper plus sulfur plus 4 oxygen. And we are supposed to have a unit charge of 0. So that is positive 2 plus 6 plus minus 8 Shinga.
0.
Exactly. So these are just few examples on how to calculate oxidation states. Yeah. Then are there questions? Okay. So if there are no questions, now we go to the end of this cool. Then another thing before I forget, someone to just mention hybridization at the end. I just say hybridization. So that I explain one thing on hybridization. Maybe just a recap on hybridization. So we did Lewis structures yesterday. Today we're going to look at characteristics of covalent bonds. No energy that is needed to break this non-can is lesser as compared to that of is it ionic bonds, all those things. So now here, this is just a part where we are going to look at geometries of molecules. So I say there's what you call the valence shell electron repulsion theory. Valence shell electron repulsion theory. It's called the Vespers theory. So in the Vespers theory, we're just looking at this is called the la valence shell electron pair repulsion. So we're just looking at how molecules are oriented in space when they are bonded to Shana. This is how molecules are supposed to be seen or visualized. This is how molecules are supposed to be seen, visualized. So, Gypsy réancien sur la géométrie spatiale de l'espace. We are looking at how molecules are oriented in space. We're looking at how molecules are oriented in space. Then you'll be seeing to my formulas that I'll be showing you as we go on. N will represent the number of, that is the direction of the liaison, and P will represent the doublet. A doublet is what you call it? It's a lone pair of electrons. It's a lone pair of electrons. And the format is going to be A, X, N to represent then the direction de liaison, and P to represent nombre de doublet. So we have these lobes here. Some molecules will form linéaire, that is sp3 hybridisation. Some will form trigonal, which is sp2. Then some will form tetraedric, which is sp3. Then you have bipyramid trigonal, which is is it D? Something. Someone asked this question about hybridization. It should be D. What did you ask Samuel last time? D what? Is it DSP? Should be this hybridization. And you have the last one, which is octaedric. These are just 1, 2, 3, 4, 5. There's 5, but there are still more. So N, that is, there are two non-constitutive. That is N, nombre de direction du liaison. So we have how many directions? We have 2 directions. And how many nombre doublet non lié? We have 0. So say 2 plus 0 est égal à juge, which is the same thing here. We have 3 directions, and we have non-lion. It's going to give 3. NC the suite. Now I'm going to show you molecules that really form this type of liaisons, or maybe the type of geometric structures. So the first one here, you have is it a hydrogen nitride? Hydrogen nitride. This one here, you have helium, you have beryllium, which is a hydrogen, beryllium hydride. This is beryllium with 2 hydrogen atoms, and you also have carbon dioxide. So they form a 180 degrees orientation. That is the angle 180 degrees orientation. Then X, which is what is X here? If you are following, X, shinga X. There's Tregonga. What is X? N is what you're seeing here. Nothing changes. Yep. The X you're seeing are these atoms that are bonding. The atoms that are bonding here are these, what you're seeing, the X's and all those things. So the N, sorry, I forgot to mention, it was N, not X. N represents the directions du liaison. The directions du liaison. So there are 2 directions. There is one that's going that side, and there's the other one going in this direction. So there are 2. Then the number of electrons that are non-Lyon. The number of electrons that are non-Lyon. How many? There is 0. There is totally 0 electrons that are non-Lyon. And when you add 0 plus 2, you're going to have la figure de reposition linéaire 2 plus P, which is 2. This is N plus P, which is 0. Era per Z, era per 2. It will give 2. It will give 2. Then the A is just to represent the central atom. The A is just to represent the central atom. Then we have that is geometry triagonal with AX3, A0. Same principle. N is equals to the X, please. The X represents the other atoms that are bonding to the central atom. The A is the central atom. Like this is, if this is sodium, then it is bonded to 3 chlorine atoms. Chlorine. We are saying we are representing sodium with the letter A, and representing the 3 other chlorines with X. In other words, the formula would be NaCl3. So it's la même chose. Now we're just showing it in this type of representation. It's called formule de gypsy. Now, so here the geometry we have is trigonal, trigonal. And an example of a compound that forms a trigonal is fluor de brom. Fluor de brom. So it forms an angle of 120 degrees between the adjacent fluorine atoms. Then the central atom, like we are seeing here, is Bo. It's Bo, which is a boron. Then the adjacent atoms, which are the X's here, you are seeing, is fluorine. There are 3 of them. So N is equals to 3. And the liaison, non-liaison, the, what do you call them? Lone pairs. It does not have any lone pairs. It does not have any lone pairs. So it is equals to 0. And therefore, N, which is 3 plus P, which is the number of non-linear, is equals to 3. So you have N 3 plus 0 égale à 3. Égale à 3. So another example is formyl aldehyde, which is known as methanol. Methanol. It also forms an angle of 120 degrees. Yeah. Then here it forms an angle of 122 degrees. So it means there is a bit of tilting. There is a bit of tilting. Yeah, there is a bit of tilting. Then we have another one here that is geometry QD. So the QD here is l'atome central, which is SN, should be tin and bonded to 2 chlorine atoms. Bonded to 2 chlorine atoms. So when you see this like a umbrella thingy and you have 2 electrons, in these diagrams, the diagram, the gypsy, all these diagrams you're going to see. If you see a calob thingy on top with 2 electrons, that shows that this is the lone pair electrons. So in our case, we have is it SN, which is tin, as our metal central, and chlorine, which is our non-metal adjacent, and has got 2 directions. It has got 2 directions. That is this one here and the other one there. So which is X is equals to N is equals to 2, and E, that is the one that shows the electron non-Lyon, represented by P subscript. We have 2 plus 1. That is N2 plus 1. We're going to have a 3. So that is, we have the direction that is N is equals to 2. The chlorines, that is 1 chlorine there and the other chlorine there, that's 2. Then we have 1 electron or 1 pair of electrons that are involved, but are not involved in any liaison. They are not involved in any liaison. And the angle is less than 120 degrees. Less than 120 degrees. So these structures, you are supposed to know them, because a question might come and say, okay, you have been given a molecule of so and so. What type of geometry is it going to form? So you're supposed to know this one is going to form trigonal plane, and you're supposed to also know the angles between the molecules. You're supposed to know the angles between the molecules or the atoms. So then we have geometry tetrahedric, which is going to be an example. We have methane. So the atom central is carbon. The X here is hydrogen, and we have 4 hydrogen atoms, and there is no lone pair of electrons. There are no lone electrons, and therefore, when we want to calculate la figure de repulsion? Yeah, figure de repulsion. That is tetrahedric. It will be N, which is 4 plus P, which is 0, which is going to give us a 4. N, which is 4, plus P, there are no lone electrons, will give us a 4. They'll give us a 4. That, and an angle of 109.5 degrees. So this is where we had the sp3 hybridization. sp3 hybridization. Then we have another one that is geometry pyramid trigonal. We have geometry pyramid trigonal. So the angle that exists in the pyramid trigonal is less than 109 degrees, and therefore it also forms a pair of electrons that are not involved in any liaison. That is 1. This is the one here. The P is equals to 1, and forms or maybe has a direction of 3 other hydrogen or other atoms. That is hydrogen in this case. 1, 2, 3. You have 3 hydrogen atoms, and therefore la figure de répulsion tétraédrique ou bien la géométrie pyramide trigonale would be 3, which is n plus 1, which will give 4. It will be 3 plus n plus p, sorry, which is 1, will give a 4. Then we have la géométrie codée, and alpha is less than 109 degrees. An example is water. An example is water. And please, these bond angles, you are supposed to master them. You are supposed to master them. They can just give you and say, please draw a structure that has a bond angle of 109.5 degrees. Then you are also supposed to give maybe the type of hybridization that it forms. So if they tell you that, it means you're looking at the geometry tetrahedric, and an example is methane. An example is methane, or any other alkane. Any other alkane will still form the sp3 hybridization. Yeah. Then we have, is it water? The angle between the adjacent hydrogen atoms is less than 109 degrees. Then there are two pairs of lone electrons. So there are 2 of them. There's this one here, 1, and there's another one there. So this is P is equals to 2. Then we also have 2 other hydrogen atoms in this direction. We have 2 other hydrogen atoms in this direction. And the l'atome central is oxygen. L'atome central is oxygen. L'atome central is oxygen. It will be 2 for the 2 hydrogens there that are adjacent, plus the 2 that are lone, plus the 2 that are lone. It will give a 4. Then we have geometry B pyramide trigonale. We have this is a phosphorus pentachloride. Donc l'atome central is phosphorus, which is represented by the letter A, and X in our case here is the chlorine atom. The chlorine atom, and there are 5 of them. That is 1, 2, 3, 4, 5, and the number of electrons that are non-Lyon. In our case, we have 0 electrons that are non-Lyon, and therefore la figure de répulsion bipyramide trigonale will be n is equals to 5 plus p is equals to 0, and we are going to have a5. La géométrie forme blanchoir. It will be, we have how many adjacents? That is 1, 2, 3, 4. So in other words, the n is representing the number of atoms that are bonded to the atom central. The n is representing the atoms that are bonded to the atom central. So there's no need of counting. You just look at them or look at the formula, then you'll be like, okay, this is how it's supposed to be. So we have tetrafluoro, sulfur tetra fluoride. Then the angles here, you have 101.5, you have 86.8 degrees, and it only forms a single lone pair. It only forms a single lone pair. And therefore, the directions are 1, 2, 3, 4. That is X4, and only 1 pair of electrons. And therefore, the figure de forme blanchoir will be equals to blanchoir will be equals to 5 as well. It will be equals to 5. Then geometry honte. You have bromine 3 fluoride. Bromine 3 fluoride. Mchipunda sisi unaniwasha. Sisi. Yeah, but blanchoir, I can lie, why is that? Yeah, but we continue. So then we have is it the last one? Okay, we still have a lot there. You guys are we still have a lot of geometries you're supposed to know. All of them you're supposed to master them. So there is where are we? We're here. Geometry on T. There is what you're calling bromine trifluoride. So you have three adjacent fluorine atoms, 1, 2, 3, and you have 2 lone electrons, 2 pair of lone electrons, that is 1, 2. And our P will be equals to 2, and our N will be equals to 3. And therefore, la figure de répulsion, géométrie on T est égale à 5. Est égale à 5. Then we have géométrie linéaire. Géométrie linéaire. Now, géométrie linéaire, we have Leon. This is is it an ion of iodine when it forms is it a tri molecule, when it forms a triatom. It forms a triatom. So we are going to have how many? That is 1, 2 atoms of iodine that are adjacent, and the central atom is still iodine. The central atom is still iodine, and has 1, 2, 3 pairs of the lone electrons, and therefore P will be equals to 3, and the adjacent iodine atoms are 2. Therefore, it will have la figure de répulsion géométrie linéaire, that is 2 plus 3, which is equals to 5, which is equals to 5. So in other words, what I would advise you guys can do for these geometries is you can arrange them in order of la figure de répulsion. The ones that have got a repulsion of 4, you arrange them, all of them together. The ones that have a repulsion of 3, same principle. Those that have a repulsion of 2, same principle. And also note the bond angles. Also note the bond angles. Then we have figure de répulsion octaédrique. Figure de répulsion octaédrique. So we have sulfur. This is sulfur hexafluoride. So it forms how many? That's 6 adjacent fluorine atoms. 6 adjacent fluorine atoms. And when we draw our what's this? Our formula de Gibbs-Lee, it will be l'atome central A with X6, that is for the adjacent fluoride atoms, and there is no electron that is lone. There is no electron that is lone, and the bond angle for the geometry octaedric is 90 degrees. Is 90 degrees. Then now we have our what is it? Is it iodine pentafluoride? We have iodine pentafluoride. It forms a geometry pyramid, a base carré. So it will be, a base carré is like a square. So we have 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. Adjacent fluorine atoms, and we have 1 lone pair. It also forms an angle approximately equals to 90 degrees. An angle that is approximately equals to 90 degrees. And the last one is hexene. Xenon pentafluoride. Xenon pentafluoride. So this one forms also a repulsion, that is geometry à plan carré with n is equals to 4. 1, 2, 3, 4. And how many? P is equals to 2. That is 1, 2. We're going to have 90 as our angle between the adjacent fluorine atoms, including the what you call them, the lone pair electrons. So guys, this marks the end of our class for Chimie Générale. Chimie, Générale. Then I mentioned something about hybridization. So basically, when they ask a question on hybridization, what they just mean is, maybe just show you what they mean. When you're talking about hybridization, with those structures, is it clear with those structures? Structure, just gun them. Is it clear with those structures? How to create the formula, the gypsy, and all those? Yes, c'est clair.
And kuswata che. The possibility it is.
Ah bon. Yeah, ndipo chitache, nguswata che. But you should also, at least even if you are sweating, you should also know that okay, kulia soso na soso, kulia soso na soso, kulia soso na soso. At least was watching a video at that, right? Where is it? When you hear something like hybridization, please, wherever you go, when someone says hybridization, this is what they mean. When there is hybridization, there is going to be degeneration. There is going to be movement. Now, like I said yesterday, I said some diagrams will not, like diagram energetic won't be respecting the energy fluctuations. But when there is energy degeneration, if there's degeneration of energy, it means two shells have now come in the same, they have now the same energy, they have the same energy. So take for instance, if you have the D block, we are saying the D block is in the lower energy as compared to the what's this? The D block, the 3D block here. Normalement, if we were to draw it, it would be like that. Would have one there. That is for the 3S. Let me just say for 3P. Then we have the other one, which is 4S. And we have the D. I'll just raise straight line for the 3D. So if there is hybridization, the reason why there is hybridization is because there is a degeneration of these energy levels. So if there is hybridization, it means we are going to have this now. D, like that. So the energy is now, the energy of the 4S and the energy of the 3D have now become equal. They have now become equal. So this is what they're trying to show here. This is what they're trying to show here. And please take note, for your core, I think, for your class, for you guys, for Chimie Générale, the only types of hybridization I guess you only do are the three. That is sp3, hybridization, sp2, and sp. Then another thing that maybe I might have forgotten to tell you is that hydrogen will never ever form a hybrid. Hydrogen will never ever form a hybrid. The reason being is just very simple. The reason being is hydrogen only has one electron, and it only has one orbital. It only has the s orbital. For you to form a hybrid, like I gave an example last time, you are supposed to have the merging of two different species for you to form another species. Now you only have one hydrogen atom and only having one shell. So therefore, it will be hard for you to form a hybrid. Then I also asked a question last time to say, is it possible for the carbon atom to, I'm like making a summary of everything now. There's a question I asked you guys. There's only one person that answered that question. Is it one person? Is it Kennedy? Are you around, Mr. Kennedy? Is Kennedy around?
No, he's not.
I think I answered this question. I gave this response to a lot of people. There's a question I asked on, is it possible for the hydrogen atom to form, four bonds? Is it possible for the hydrogen atom to form 4 bonds? What was your response, you guys? What did you say? You said, some said it's possible, some said it's impossible, some said no, I don't know. But the answer is, it is impossible for the hydrogen atom to form what is this? The 4th liaison. The reason is simple. It all comes back to hybridization. It all comes back to hybridization. So because the least or the highest hybridization that you can go is sp3. Oh, sp3 is the highest. Maybe sp is the lowest. Sp is just the hybridization of one s bond or beyond one s orbital and the hybridization of another p orbital. Just two. Those are the last ones, and they're all sharing two electrons. And we say that there's going to be an aspect of neutrality, and you have the formation of the sp hybridization. Now, when you have the formation of another liaison, it now disqualifies hybridization. Now it comes back to the case of hydrogen. You cannot have hybridization between two s orbitals. You can't have hybridization between two s orbitals. You're supposed to have hybridization between an s orbital and another orbital that is superior in energy. You're supposed to have a hybrid of two different energy levels, the s orbital maybe and the d orbital, in a case where something like that can happen. But you're supposed to have at least degeneration de l'énergie of the s orbital and of another orbital that is higher in energy, be it the p, be it the d, be it the f. But the lowest energy that we have, if we are at s in reference to the energies, the p is the closest. So our degeneration will be in regards to the p orbital. But for the d and all those things, we are going to have maybe the p orbital degenerating with the d orbital, the f orbital generating with a d orbital, etc. That is the why you have the formation of the d, is it xy hybridization, the d, etc. hybridization. Yeah. So is it clear? I'm looking for an exercise that maybe can help you guys with molecular mass. This one that I give. Kondo, I think you have it, isn't it? The one you're supposed to calculate from relative masses. Kondo naenda. Okay. Yeah, so you guys, yeah, this is the end of our Chimie Mineral. So Chimie, what's this? Chimie en solution. So if there are any questions, please, you can ask. Yeah. So I'll hand over to Mr.